Hey guys, Mrs. Dance here. So we're on lesson 5. Now this is like a big, important lesson. You have to pay very close attention. You can see what the objective is. You really do need to write down all of those words. They're all so important, and it would be great to look back at what you wrote for your objective to even like remind you of how to do these things called piecewise functions. Um, you can see my number 2 of getting ready. I like put a line through it. It said, cut your index card in half and wait for further instruction. You'll see that when I'm graphing, I use index cards to like cover up part of the graph so that I could connect the points that I'm supposed to connect. So it doesn't necessarily have to be an index card. You'll see since I'm doing it on a computer, I'm just like using, two windows to hide parts of something. You could use two pieces of paper, you could use your hands, but I'm going to show you using what I'm going to use to represent an index card. And I am going to do the do now with you and the development, and then you get to start your classwork and homework. So you're really finishing uh, the lesson for homework. So this do now is review of our absolute value functions. And the first thing it's asking us to do is rewrite in vertex form. So remember, we don't like this 3 as a coefficient of x inside the absolute value symbols. So to rewrite it, you will undistribute, and then you take the absolute value of that 3, which is 3. You keep the x minus 3 in absolute value signs, and now it's in vertex form. I know that the vertex is at 3, 2. I also know, because of this rate of change here, 3, that it's a narrow V opening upward. It goes up 3 and to the right 1, or up 3 and to the left 1 in order to make it a V-like shape. Now, in order to evaluate this function, sorry, remember the number in parentheses here, that's your input, which really means it's your x value. So they're asking you, when the x value is 2, evaluate it, which means find the y value. You should be able to tell from looking at your graph. If I go to the x value of 2 and find a point that corresponds to it on the graph, I can see that that point is at 2, 5. Therefore, f of 2 equals 5. They give you the input, you're trying to find the output. Remember that output is your y value. So when I ask for f of 5, go look at 5 on the x-axis, what point corresponds to it, and name that point. It's 5, 8. Therefore, the output would be 8. F of 5 equals 8. When f is 3, it corresponds to this point here, which is 3, 2. So our output is 2. When f is negative 10, here's negative 10. And now you might be thinking, oh, we have a problem. Like, what point corresponds to negative 10? I have to tell you that there is a point that corresponds to it, because this function does have an arrow. It is a very steep V, so it's going up at a pretty big rate. Therefore, it's going to be some high number um, of y where x is -10. And I can't see it on the graph. So when you can't see something on the graph, then you're going to evaluate it algebraically. Um, I'll use the original function they gave me and substitute in a -10 in place of x. So I get inside the absolute value -30 minus 9, which means inside the absolute value it's a -39. And the absolute value of 39, -39 is 39. And then 39 minus 2 is 37. So f of -10 equals 37. So that means that there's a point on this graph that's at -10 comma 37. And it makes sense. I knew it was going to be a very large number. Now, I substituted the -10 into the original equation. I could have been able to substitute it into my vertex form also, and I would have gotten the same answer. You could also just use your graphing calculator to do all of this. And there's really a few ways you could use your graphing calculator. You could enter the original function into your y equals, and then you can look at your table of values and scroll to where x is -10. And you can see it is 37. Remember, you can enter your vertex form in here as well, and it helps you check yourself to make sure the function you wrote is mathematically equivalent to the original function. Take a look at the table. All the numbers are identical. So you could have even just entered it in on your home screen, but remember you have this tool that you can use. So now let's get into what a piecewise function is. Some people actually say that we can call an absolute value function a piecewise function. Just think of the name, piecewise function. What they're trying to say is that we're going to be graphing pieces, and all these pieces put together make one function. Well, can you agree with me that maybe this absolute value graph can be looked at as two pieces? Maybe one linear function here and another linear function here that just so happen to be put together to be a V-like shape. It really is two pieces of linear functions. So that's how come some people say, oh, well, an absolute value graph can be written as a piecewise function. And you'll see that in a moment. So this piecewise function had a typo in your book. If you could please make sure you change your function to look like mine. And I'm going to show you how they graphed it. So notice, looks like there's two pieces, right? It's got the squiggly bracket here to show that there's a few things that we need to graph. And there are two pieces that need to be graphed. And then there's this strange stuff over here that we haven't seen with any of our functions. And that's because each piece of this function only exists in a certain part of the graph. And this is where you really need your thinking caps on, and definitely ask questions next time you see me. This first piece is linear. The slope is 2 over 1, and the y-intercept is -1. So if we were to graph just that, like we used to in the past, we would start at -1, and we would go up to the right one. Just take a look at my graph. Right now, all you're doing is watching, because the function really is already graphed for you. Do you see that some of my green dots really are landing on some pieces of graph that are already attached with the line? So what we used to do is draw a full line with the arrows. So now we're not drawing a full line with arrows, and that's because we're only graphing a piece of this function. So I'm going to leave my green dots because I started at the y-intercept and then did my slope. It's this second part of the function. Let me get another color here. It's this that tells me which dots I'm supposed to connect. I'm supposed to connect the dots that I plotted from -4 to 1 for the x values from -4 to 1. And this is where those index cards come in. So I'm going to use these windows as an index card. So I have to connect the points that I plotted that are between -4 and 1 on the x-axis. -4 and 1 on the x-axis. So I'm going to use this as my index card and cover up x's that are not between -4 and 1. I need my other index card. And right there, see these green dots? These are the dots that need to be connected. Of course, as soon as I touch my screen, my index cards go away. So it's going to make it difficult for me to show you which ones to connect, but you can see the ones that are connected. And I just attached it in red. And then you erase the other dots that are not necessary. So, like I said, they already graphed it for you. They did connect the correct points, and they got this one piece. Look at their endpoints at each side. There are closed circles at each side of this function. No arrows anymore. It stops at each end here. And then how did they get the other piece? Well, the slope of the other piece is 1, and the y-intercept is 3. So if I start at 3 and go up 1 over 1, you can see I get points on this function. They didn't connect them all, though. Why didn't they connect them all? Well, that's because it doesn't exist everywhere. It only exists for the x's that are greater than 1. So if you use those index cards again, I said it exists for x's greater than 1. So none of these x's here. And now I actually can't use this second index card because it says x greater than 1. So it doesn't stop at an x. So I'm not going to use this second index card. And now you could see why the points that they attached, they did. It's only this piece here for the x's that are greater than 1. And those other points I had plotted should get erased. Now notice on the second piece, there's an open circle. And that's because of our inequalities. Right here, a greater than means put an open circle. The top piece had less than or equal to. Equal to is closed circle, not equal to is open circle. So in order for something to be a function, remember each input can only have one output. So there's something very important in this graph. You can see that it looks like there's 2 points, one above each other, which actually makes it not a function. But since one is closed and one is open, this top circle really is just a placeholder. It's not an actual point. If I asked what is the y value for an x value of 1, for an x value of 1, the y value in this function is at 1. It's not at 4 because that's an open circle. So this really is something that is going to take practice. You'll see that we're going to do a few lessons of piecewise functions, but this is how you do it. You graph each piece, you only connect some of the points, you connect the points that it tells you to in this second part of the function where it tells you which x values it exists. Of course, we can do this evaluation like we did with the do now. F of -3, here's -3. It corresponds to this point. Oh, it's -7. F of 1, we just talked about it. It corresponds to the closed circle, not the open circle. So f of 1 is at 1. And then f of 4 corresponds to this point. F of 4 is 7. You could do it by substituting into the function, but be careful. You have to substitute it into the correct function then. When it asks you, again, part A, what is f of -3? Remember, -3 is an x value. -3 does fall between -4 and 1, so I can plug the -3 into this top piece. 2 times -3 is -6. -6 minus 1 is -7. Check. It actually does fit in that first piece. When I'm doing f of 1, what piece does f of 1 exist in? Where does x equal 1 exist? It does exist right here, right? It says also equal to 1. Here it doesn't equal 1. It has to be greater than 1. So f of 1 exists in this top piece. If I plug a 1 into that x, 2 times 1 is 2, and then take away 1 is 1. Check. It worked by substituting in. And then finally, if I wanted to substitute in that last one to evaluate f of 4, where does 4 exist? Well, 4 does not exist between -4 and 1. So 4 is greater than 1, so it exists in the second piece. So I have to plug it into this second piece in order to evaluate it algebraically. What is 4 plus 3? It is 7. So just have to be very careful if you're going to do it algebraically as to what piece do you plug it into. So let's practice graphing. You can see there are 2 pieces here. Just graph one piece at a time. Plot a bunch of points, but only connect the ones where it exists. So the slope is a half. The y-intercept's -1. So we start at -1. And we go up 1 over 2. So I'm going to plot a bunch of points. And I'm going to wind up erasing some of them. My index card idea, I'm having a really hard time doing it on the computer. If I was doing it by hand, I could take actual index cards and lay it on the screen. So I'm just going to mentally talk about which points I'm supposed to connect. I'm supposed to connect the points that are between when x is -6 to when x is 2. Maybe I'll darken in those 2 points in another color to make it stand out for you. When x is -6, we're at this point. When x is 2, we're at that point. So let's connect the points between those 2 blue pieces I did. I kind of like that better than my index card idea. I'm going to erase these orange points that didn't get connected. I'm not going to move on yet. I have to check my open circle, closed circle stuff. Do you see at -6, it should be an open circle because it just says less than. At 2, it should be a closed circle because it's less than or equal to. So let's make sure it's a closed circle at 2 and make sure it's an open circle at the -6. There's my first piece. Okay, so now I'm going to graph the second piece. The second piece has a slope of -2 and a y-intercept of 1. So let's start at 1. Since the slope is -2, you go down to right 1. Now, as soon as I'm crossing over this piece I already drew, I know that those are not going to be pieces I connect. Remember, to be a function, each input can only have one output, which means you can never have 2 points one above each other on a graph. So these points that are landing above the blue graph, I know I'm going to erase, but I'm just going to plot them for now until I actually do connect the pieces that truly show where it exists. It exists between 2 and 4. So I'm going to change to my blue pen again. Between when x is 2, that's this point, to when x is 4, which is this point. I have to connect the points that are in between there. Erase those other points that didn't get connected. And check your open circle, closed circle. Notice it should be open circle at both ends. So I'm actually going to change this to an open circle and an open circle. There we go. So now let's talk about domain and range. Remember, I said that we'd be practicing domain and range practically all year. The domain are the x values where this function exists. If I look from left to right, those are my domain. So looking this way, do you agree that the function starts here and ends here? The domain of this function starts at -6, ends at 4. Now you just have to figure out, if you're doing interval notation, do I use a bracket or a parenthesis? Since it's open circles at each end, it's parentheses at each end. So in interval notation, a domain is from -6 to 4. I could have written it using like inequality notation, or what we call set builder notation. I could have said that it exists for the x is between -6 and 4, and it's not equal to, so I just put less than signs. So that's allowed also. If I were to talk about the range, I'm going to draw some lines from the lowest that this function goes to the highest that the function goes to. So the range exists from y's between -7 to 0. It's a parenthesis at -7 because it's an open circle, but it's a bracket at 0 because it's a closed circle. So you can draw these lines on your graph to help you with domain and range. Domain are from what x value to what x value, and range from what y value to what y value. I think I'm just going to do one more function. I guess I'll do example 3. We'll see how my time is if I do any more. Example 3, we actually call a step function, and you'll see why we call this a step function. Notice that there are 3 pieces, and these pieces are just constants, right? It's just the number 2, and it's just the number 3, and it's just the number 4. I don't see the variable x. So this is actually reminding me of my horizontal lines. If I just wrote y equals 2, you would know that that's a horizontal line at 2. If I wrote just y equals 3, then that would be a horizontal line at 3. If I wrote y equals 4, then that would be a horizontal line at 4. That's really what this is saying. It's just that it's not a whole line. Remember, these are pieces. So it does relate to y equals 2, y equals 3, and y equals 4, but we don't put like the arrows. There's going to be some open circle, closed circles. It only exists at certain spots. So let's see. So the first piece is a horizontal line at where y equals 2, but it's not the whole line. It's the line from when x is -2 to when x is 0, and the other part of the line gets erased from x is -2 to x is 0. Do you notice closed circles should be at -2, open circles should be at 0. So let me just make sure that is true as well. The next piece was a horizontal line at 3, but it doesn't exist everywhere. Like if I draw this horizontal line, I know I'm going to have to erase some of the stuff that's above the horizontal line that's already there. It exists from 0 to 2. Here's where x is 0. Here's where x is 2. You can erase the other pieces of the line. And notice it will be a closed circle at 0 and an open circle at 2. So just let me make that clear. And then the last piece, when y is 4, exists from between x being 2 to x at 4, closed circle at 2, open circle at 4. So I told you that they call this a step function because doesn't it look like steps? Like you can step on each piece to go up the stairs. So let's talk about domain and range again. I'm going to use different colors to show that the domain starts here and ends here. The domain is from -2 to 4. It's a closed circle at -2 and an open circle at 4. I'm going to erase those lines because now I'm going to draw some kind of lines for my range. Actually, range on this one is a bit tricky. Range isn't continuous. And what I mean by continuous, there's gaps between my range. The range only exists at 3 places. The range exists at 2 and at 3 and at 4. Those are the only places it exists. I can't say continuously from 2 to 4 because it doesn't exist at like 2.5. It doesn't exist at 3.5. So the way I'm going to write this is at 3 different places using squiggly brackets. Remember, these brackets represent set notation. So it exists at 2. It exists at 3. And it exists at 4. So sometimes your domain or range is not continuous. It just exists at distinct places. I am going to do this last one. I know this video is extra long, but I think it's important because notice there is going to be a question, what's it look like? So if we graph this first piece, we start at the y-intercept 7, we go up 2/1. I like that I've decided not to use index cards. I guess we kind of learn new things with new technology. I used to do this by hand and not teach through a video. So now I see teaching by video. These index cards didn't work for me. I do like picking another color and darkening in the points where it exists. It exists for all x's greater than or equal to -3. So here's where x is -3. It equals it, and the x is greater than it, go this way. So I am going to put an arrow on this one, erase these other points that I plotted. There's one piece. Now let's do the other piece. I'm going to go back to my blue, and I start at -5, and I'm going to go down to right 1. Remember, the opposite of down to right 1 is up to left 1. And where does this exist? So I'm going to get my red marker. It exists for x's that are less than -3. So again, here's my -3. X is less than -3, go that way, right? So I connect the points going that way. And I erase my other points. So now we know why it asked the question, what does this look like? Doesn't it look like an absolute value function? So since it looks like an absolute value function, I can write a different function that's equivalent to this. So I'm going to write my absolute value function in vertex form. It was up 2 over 1. The vertex is at -3, 1. So there I go in vertex form. This shows a vertex of -3, 1. This shows a narrow v going up 2 over 1. There will be a question similar to this on future tests or quizzes. So it was an important question to do. So one of my lengthier videos, I started off, I'll admit, a bit kind of like it was a bit slow going because I was trying to use index cards, trying to show you that you could cover up pieces of the graph, but you can do it visually using maybe different colors. Maybe that's how you're going to want to do it yourself. It's called a piecewise function because we are graphing pieces, and we still will be talking about domain and range, and you have to be careful. So your homework is these next few pages. There's only 6 questions. I think I'm going to have a homework helper video. I think I do number 4 in my homework helper, so take a look at it. But just do it carefully, and I'll talk to you soon. See ya. Bye.